In my last video, I successfully machined a Nozzle Guide Vane in Inconel 718, but I ruined it in the final operation. So now, I have to do it all over again. This time, I'm trying something new, a 4mm ceramic end mill that cost me only €18. Sounds promising, right? Well, ceramic milling turned out to be much harder than expected. Hi, I'm Alfonso. I spent over 40 years as an engineer in the space industry, and now I share my passion for CNC machining and DIY turbine projects here on this channel. The nozzle guide vane must be made from Inconel 718, a high-temperature nickel alloy used in real turbine engines. For turning operations, I'll use Tech inserts designed for S-class materials. This part requires two main operations. First turning, and then milling the internal vanes. Machining Inconel 718 on a mini lathe is always a challenge. I'm running at just 80 revolutions per minute with a feed of 0.05mm per revolution. Before touching the real part, I decided to run a test. According to the manufacturer, the recommended cutting speed requires very high spindle speeds. Fortunately, my spindle can reach 24,000 revolutions per minute, so I was able to run within the expected range. I selected a feed rate of 2,150mm per minute and a very small depth of cut, just 0.2mm. And the results were quite impressive. Now it's time for the real part. This time, I decided to reduce the feed rate significantly up to 600mm per minute. I wanted to test a more conservative approach for this geometry. At this point, I started to question something important. I had already tested the tool successfully at high speed, so why was it failing now? So I went back closer to the original strategy, high feed rate now, 3,000mm per minute, and improved chip evacuation using compressed air. But once again, tool failure? This suggests the issue is not just cutting speed. It could be related to tool engagement. Machine rigidity, or localized stress in sharp corners. I purchased new bits, and waiting for the parts, I decided to finish this side with a carbide end mill. Even after adjusting parameters, reducing speed, changing feed rates, the behaviour remained inconsistent: poor cutting, excessive burrs, and repeated tool breakage. With no ceramic tools left, I went back to what I know works: carbide end mills. Much slower, but reliable. In DIY machining, time is not always the priority. Finishing the part is, because the 3mm end mill can't reach the edge of the blade, I need to finish by grinding the part. Finally, I need to taper the M3 holes. This process requires very captions to not break the tool. Honestly, I can't recommend ceramic milling for this process, at least not in my setup. Even running at 24,000 revolutions per minute, which is within the recommended range, I couldn't achieve a stable and repeatable result. This suggests that ceramic tools are extremely sensitive to factors beyond just cutting speed. Machine rigidity, toolpath strategy, and engagement conditions seem to play a critical role. Carbide tools were much slower, but far more predictable and reliable. And for a DIY project, that's what really matters. If you have experience with ceramic tools, let me know in the comments. I'd really like to understand this better. If you found this useful, consider subscribing, and don't miss part 7 of this turbine project. Thanks for watching. See you in the next one.